So this is for Algebra 1, Semester A, Unit 1, Graphs of Nonlinear Relationships. And I'm going to go over the guided notes and then some practice problems from the application section. So nonlinear means it's not linear, not a line. And nonlinear equation would be like a parabola or something that's exponential or a circle. So I think we're mostly going to focus on exponential here. And if I were to zoom in on this graph, you can see that it has a curve to it. So the number of fish exponentially increases with the amount of time that there is. And originally there are 500 fish in the pond if we're looking at the y-intercept right here. So according to the graph, the pond initially has 500 fish. That's the y-intercept. The x-axis, that's the one across the bottom, shows the time in months, and the y-axis, that's the one that goes up and down, shows the number of fish. Okay, so the number of fish is increasing by a factor of 1.3 each month. We are multiplying this, which is the same as growing at a rate of what? So 130%. Just multiply it by 100 to make it a percent. The graph shows the number of fish increases by increases by 130% each month. So not a line, it is exponential. Okay, so here we have another graph, and it's showing two different lines. So I'm not going to fill in the blanks for this one. I'm just going to describe what I see on the graph. The blue line is a checking account, okay? So I'm looking at this graph, and the blue line is a checking account. This blue line, the checking account, is a linear function. It has a slope to it. I can see it's a straight line. It goes up 1 over 2, up 1 over 2. So this is a line. And the original amount in the checking account is $7,000. So after, let me see what the time is down here. So each thing is a year. So after 2 years, there's $8,000. And after 4 years, there's $9,000. So this has like a steady increase to it, this checking account. Okay. Savings account, however, work a little differently because they have a percentage rate where you can earn interest. So the savings account, the red line, is an exponential function. And if you notice, it starts at, where does it start at? I need to scroll down. It starts at $5,000, but it increases at a quicker rate than the checking account does because of the exponential interest. And you can see where they cross right here. So they both have $10,000 after 6 years, but past 6 years, the savings account is going to earn a lot more money a lot quicker than the checking account would because it is exponential. Okay, so describe the differences between the graphs based on the unit scales and intervals that show the data. Erica's app starts with 2 downloads, and then the number of downloads doubles each minute after the launch. So I'm pretty sure these are going to show the same data, but the intervals and stuff are going to be different. So if we look at the first one, time for all of them is minutes across the bottom on the x-axis, and then the number of downloads is on the y-axis up and down. And it appears the first two are exponential. It starts off kind of slow, and then after 6 minutes, it takes a sharp increase and then goes quickly. The number of downloads increases quickly, like the higher it gets. So that's showing, like thousands of downloads in 10 minutes. If we go to the second graph, the number of downloads only goes up to the number 24. And the minutes only goes up to 6. So this is not a very good representation of I think her experiment, because really this only goes to like 4 minutes right here. It's not a good thorough understanding of everything that's going on. The last graph, number 3, again, doesn't have very many downloads. It only goes up to 12, which if you have an app or a music video or something, that's not a good representation. It needs to be in the thousands, right? And then the time in minutes, it doesn't even go to a full minute. It's at 0.7. So this is way too small of a scale. You can't really tell. And it looks like, just based on this, it looks like a line, but we know that it's not. The first graph is the best representation of her data. Sorry, I keep zooming in and out. Okay, so exponential decay. Here is another way that you can use exponential data. And here we have time in minutes and the number of disease cells. Time is the independent variable. It's not going to be affected. And the disease cells is the dependent variable. So that is what is changing with the amount of time. So the independent variable is time and will be on the x-axis. The dependent variable is the disease cells and will be on the y-axis. So if we look at this function right here, as you can see, the longer it is in time, the lower the number of disease cells. And it shows like how to calculate between hours and minutes. So 4 hours, there's 60 minutes per hour. 4 times 60 is 240. That's where this is right here. And then they broke up the intervals based on that. So every grid unit will represent 1 hour. And to find the pattern in the exponential functions, it's not going to be adding or subtracting something like you would with a slope. You're multiplying and dividing. So if we're looking at the data, like the 0.02, the 0.14, the 0.26, the independent variables are going up by 1 each time, but the linear, you're going up by 2 each time. So it's increasing at a constant rate of 2. And an exponential, like a line would be like up 2 over 1, up 2 over 1, like the slope. But an exponential difference is like if you're multiplying or dividing by something. So here it's showing that you're multiplying by 2 each time. 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's going up at a, like this would be like a line, and this is going to be your exponential with the curve where it increases sharply really quickly. Okay. I'm zoomed in and I can't zoom out. Okay, that's better. So here is a example using a parabola and a baseball. Like if you throw a ball in the air, it'll go up and then it'll come down again. The vertex is the highest point of it. So the vertex is right here. And that basically is showing it's over 50 feet high at the highest point, and that happens after or over 140 feet horizontally distance. It looks like it was thrown from a height of around 4 feet, and it landed 280 feet away from where the person threw it. And this is a parabola, a negative parabola, because it's opening down. So it is important to consider the scale of the graphs. Here, these two things are showing the same information, but at different scales. So like here, the height goes to 30, but the distance, horizontal distance, isn't completely shown on the graph. And here you do see the horizontal distance, but see how the height and the horizontal distance don't really match up. It's very skewed and it goes off the top of the graph. So it should be like to like 120 here. It should be to like 120 there. So think about your scale when you're looking at graphs. It's important. And I'm going to go over a few questions on the application section just so you can get an idea of what types of questions there are. So for this one, we are comparing independent and dependent variables. An independent variable is independent. It is not changed by anything. So years since colonization is going to be the independent variable. Years are going to happen no matter what. They're not going to be affected by anything. The population is the dependent variable, and that is what is going to change based on how many years have passed. So independent is the years, and that's going to go on the x-axis. The dependent is the population, and that'll go on the y-axis. Okay, so what would be an appropriate scale for these questions? Well, obviously on the x-axis, we're going to have 1 through 5 because that is what our data is showing up here. And then on the y-axis, we have starting at 400, going to 200 and 100, 50, 25, and then 12.5. So a good scale for that would be every 100, because we have to include both 400 and down to 0 basically. And there's 5, like 1, 2, 3, 4, 5 on the x-axis. So 1, 2, 3, 4, 5 up and down on the y-axis. Okay, so here is an example. Mr. Smith owns a car that's worth $8,000. It's going to depreciate at a rate of 25% each year. So it's steadily going down at 25%. And they want to know which graph represents that. So you're going to look at, like, after the first year, it's going to be 25% less. So 6,000 is a quarter or 25% less than 8,000. After 2 years, just over 4,000 is going to be a quarter less than 6,000. After 3 years, 2 and a quarter is like 25% less. So if you multiply 4,000 times 0.25, you'll get this number. So every time you're going to multiply by 0.25 to find out what a quarter less of it is. Okay, data below shows the height of a ball after it's been thrown. Time is going to be on the x-axis on the bottom, and height is going to be up and down on the y-axis. And they want to know what the best scale is for it. So if we look at the time, it's 2, 3, 5, 7, and 9. So that's like every 2 seconds would be a good scale. And it has to go up to at least 9. So the two middle answers could be good for that. And then for the height, we're looking at between 21, okay, so 21, 26, 30. It has to go at least up to 30. This one does not go up to 30, so that's why this is a better answer, because it does go up to 30. Trying to see if there's any other type of question we haven't gone over yet. Ryan shoots an arrow upwards while he stands on top of a treehouse. The graph shows the traces the path the arrow while it's in the air. Y is the height, and X is the horizontal distance. And there's 4 stages here, A, B, C, and D. At which stage of the arrow's path does the height above the ground change at the slowest rate? So you're basically looking at the slope of these individual sections. So if we're looking at the slope of A, it's like up 2 over 1. So that's a pretty big slope. B is like up 1 over 1. C is almost horizontal, and D is a negative slope of like down 1 over 1. So C has the least amount of change out of those. Okay. So what scenario could represent this graph? It's going down and it's exponential, so it's probably a decay or a decrease of something. And the correct answer is the current through an electric circuit is halved, or it's like decreasing by half every second. So if we're starting at 50, after 1 second, it's at 25. After another second, it's at 12.5. After another second, it's just over 6. So it's decreasing by a half every second. Let me go over this one and then I'll be done. Mary initially puts $2 into a piggy bank. So our y-axis, our intercept is going to be at $2. She continues to save money such the amount of money in the piggy bank doubles each week. So after the first week, she'll have $4. After the next week, she'll have $8. So which one is going to be a good representation of this? Well, the time in weeks should be it should be like 1, 2, 3, 4 on the bottom. So one of these two. And then I think that this would be the best answer because after 1 week, she has $4. After 2 weeks, she has $8. After 3 weeks, 16. So this curve is the best representation of her savings. Okay, so this was Algebra 1A, a review of graphs of nonlinear relationships. Hope to see you soon.